Hello, statisticians. Mr. Youngsaver here from Skew the Script. Today will be the final video in our AP Stats video series. We're discussing inference for linear regression using data related to gun ownership policies in developed nations. Let's skew it. Today's lessons on inference for regression. Here's a random sample of developed nations from across the world showing their gun homicide rates per 1 million people. As you can see, one nation stands out as an outlier in this data set. Can you guess who this is? Well, this is us here in the United States. The US has a relatively high gun homicide rate compared to most developed nations, and policymakers here want to change that. Traditionally, there's been two sides to the debate about how to prevent gun homicides: gun control versus gun rights. The gun control side says that stronger background checks, an assault weapons ban, and generally lowering the firearm ownership rate would help prevent gun crimes. This side often points to countries like Japan. Japan has very strict gun control, and this side says, as a result, few people own guns, and there are few gun homicides. On the other side, there's the gun rights side. They say that if more common, law-abiding citizens own guns, it'd provide greater deterrence against criminals committing gun crimes. This side often points to countries like Germany. Germany has relatively high gun ownership rates among civilians compared to most developed nations, and this side says that as a result, criminals are too afraid to commit gun crimes, and so gun homicides are rare. So in today's key analysis, we're going to look at some data related to this issue, and we're going to ask, is there a relationship between rates of gun ownership and homicide? If you'd like to follow along using our guided notes, you can print them up from our website. So first, let's do a quick review of linear regression. The data that we have is a random sample of 19 developed nations with their civilian gun ownership rate and gun homicide rate. So how many variables do we have? We have two variables, the ownership and the homicide rate variables. And are these quantitative or categorical? Well, both variables are quantitative. When we have this situation, two variables, both quantitative, we often make a scatter plot where we visualize the relationship between those two quantitative variables. So we have here the explanatory variable, think X variable, explanatory, civilian firearm ownership rates, as explaining the response variable, the gun homicide rates. And you can see here that we have on here the two sides, what they pointed to, Japan and Germany. And both countries have fairly low gun homicide rates. They're very low on the y-axis. Yet they have very different gun ownership rates. There's a big difference on the x-axis. So what is the overall trend? That's two countries, but what about the overall trend here? Well, what we can do is we can fit the least squares regression line to model that overall trend. So if we try to describe this relationship, well, we can try and use CDOF, so you remember back from earlier unit, context, direction, outliers, form, and strength. And if you're ever asked in FRQ to describe a linear regression, you should do all of this. But today we're going to hone on these two, direction and strength. So the direction of this relationship. Well, as the X variable, gun ownership rates increase, so does the Y. We have a positive slope and therefore a positive direction. And in context, that means that as the gun ownership rates increase, the homicide rate also tends to rise. Now let's talk about strength. We see a fair amount of scatter here. This is a weak trend. The relationship between gun ownership rate and gun homicide rate is positive and weak. And it's weak because we have so much spread around our line of best fit. So often with these sorts of problems, they're going to give you a regression output table, and you have to be able to read that table and read various components of it. So let's try and use this table to figure out what the equation of this least squares regression line is. And remember, we have to describe the y-intercept and the slope in order to describe the least squares regression line. Well, the constant in the equation, the one that's not attached to an x, it's a constant, is the y-intercept. And so in this case, the y-intercept, the constant is 0.916. That means the slope, the coefficient on firearms, our x variable, is 0.046. So here is our least squares regression line. And if you were asked to interpret the slope, we would say that for every 1 unit increase in civilian firearms per 100 people, the model predicts an average increase of 0.047 gun homicides per million people. And that's describing that positive trend between these two variables. So recall that we randomly sampled these 19 countries out of all developed nations. Did we, by chance alone, happen to sample countries that made for a positive relationship? And if we had looked at all developed countries, the whole population, would that relationship, if we put them all on the graph, still be positive? Or could the direction of this line have changed? Well, we don't really know. It's a pretty weak relationship, as we described. And maybe if we added more data from the whole population, the positive trend could go away. It could even potentially turn negative or come out to be no trend at all. So let's go ahead and create a confidence interval for the slope of this line to see how confident we are that this describes a true positive relationship in the true population. So let's go ahead and make an interval for our regression slope. We're going to construct and interpret a 95% confidence interval for the population regression line. The population that we sampled from is the population of all developed nations, and we're trying to estimate beta, the true slope for the regression line if we had all developed nations on our graph. The sample that we had was the 19 developed nations that we randomly sampled. That's our sample size. And from that sample, we calculated our statistic, B, the sample regression slope. And remember, that B value was 0.047. So we're going to try and estimate beta, the slope of the population regression line, using B, the slope of the sample regression line. And we know that in order to do this, we're going to have our B that we measured plus some margin of error. And we're going to be constructing this so that we're 95% confident that we'll capture the true beta value. So as always, a confidence interval is composed of the statistic we measure plus or minus some margin of error. So the statistic plus or minus and that margin of error is always composed of two components, the critical value and then a standard error. The critical value is the number of standard errors covered in each direction to get the percent confidence. And for a mean, remember that the formula was this. It was the sample mean plus or minus the t statistic, the t critical value times the standard error. Well, for a regression slope, it's also a t interval. We're going to use that t critical value to get the percent confidence that we need plus some standard error. So how do we get those values that we need here? Well, conveniently enough, they're provided already for you in the regression output table. And the vast majority of the time on the AP exam, when you're doing some inference for regression, they're going to go ahead and give you this table. So my B value, the coefficient value that I measured in my sample was 0.047. So I'm going to plug that into my confidence interval formula. And my standard error, well, that's given here in the standard error column. And we're going to do that for my firearms slope coefficient. So the standard error for that coefficient was 0.026. So I'm going to go ahead and plug that in. And now I just need to get my t critical value. So remember, the t distribution tells you how many standard errors you should be going away. And for a normal curve, when we wanted to get 95% confidence, we would do 1.96 standard errors away. But we know that for a t distribution, it's a bit wider. And so we're going to need a bit wider of a number of standard errors in order to capture that 95% confidence. And note that for regression, it's a t distribution with the degrees of freedom being n-2, the sample size -2. So for this regression, we're going to do our 19 developed countries -2 to get our degrees of freedom. That means we have a t distribution with degrees of freedom 19 -2, which is 17. And then we can go ahead and go into our calculator to find that critical value that we need. And visualize on the screen are the commands that you need in order to do that. So when you do that, you'll see that the t critical value, the number of standard errors we need to go out to capture 95% confidence, is 2.11. And as expected, this is a bit higher than the 1.96 we needed for the narrower normal curve. So the critical value I need was 2.11. So I'm going to go ahead and plug that in here. And now it's just solving out. When you simplify this, do the positive and negative direction, we get a confidence interval from -0.01 to 0.10. So interpreting this, we are 95% confident that the interval from -0.01 to 0.10 captures the true regression slope for the linear model relating developed nations' gun ownership rates and gun homicide rates. So then we can do also the tests for regression slope. And we got our interval. We have a sense of where that true beta might fall. Now let's think about, is this convincing to us of a true linear relationship? Is there convincing evidence of a linear relationship between rates of gun ownership and rates of gun homicide in developed nations? So whenever we see that keyword convincing evidence, we're going to do a significance test. And the way we're going to formulate our hypotheses is the null is that beta equals 0. There is, in other words, no positive or negative slope here. There is no measurable relationship between my two variables, gun ownership rates and gun homicide rates. The alternative is that there is a relationship. Beta does not equal 0. There's either a positive or negative relationship to be measured here. So the null hypothesis is that there's no relationship. The alternative is that there is a relationship. And note, this is a two-sided test because this question is asking for any relationship between these two variables, not just positive or negative. And note that in the hypotheses, we're using beta and not B because we're hypothesizing about the true regression slope among all nations. We have to hypothesize about that because we haven't measured it directly. We've only measured B, our sample. So note that also another way you could write this, it's the same thing as testing if there's no correlation between the two variables. The correlation, or rho, equals 0. So note that's another way you could write these hypotheses. So you can use this interval, in fact, that we did before to figure out what the results of our tests should be. The null value, that beta equals 0, there's no relationship, is inside of our interval. So it's a plausible value. We cannot reject the null. It's plausible that there is no linear relationship, no correlation between rates of gun ownership and gun homicide in the true population. So we know that we should fail to reject the null in our case. And if you want to do that directly, everything that you need for that significance test is in this table. You have the T statistic for the coefficient, the slope for firearms right here. It's given to you in the T column. And then you also have the p-value. It's given to you right there. You don't need to do any calculations on your own. So we can analyze that p-value. Because our p-value of 0.0928 is greater than our typical alpha level of 0.05, we fail to reject the null. We do not have convincing evidence of a linear relationship between developed nations' rates of gun ownership and gun homicide. So putting this all together, we can write this out in our 4-step process and conditions. So normally when they're asking you to do a 4-step process for a linear regression problem, they're going to give you a number of things. They're going to give you the scatter plot, the regression output table, and oftentimes they'll give you a residual plot and a histogram or visualization of those residuals. So the questions they may ask is either to construct a confidence interval or to ask if there's convincing evidence of a linear relationship, which is a significance test. So we'll start with the state. For the interval, you want to state the parameter and the confidence level. We're estimating beta at 95% confidence, and we're going to define beta as the true slope of the population regression line relating rates of gun ownership and rates of gun homicide in all developed nations. If you're doing the test, the significance test, you want to state the hypotheses and the significance level. And here are our hypotheses from before. And again, the same definition of beta. And we have our alpha, our significance level. Then for the plan, you want to name your inference method and check conditions. So you want to name, I'm constructing the T interval or the T test for the slope of the regression line. And we want to check conditions. Now note, this test, this inference procedures, has the most conditions of any inference method in AP Stats. So let's get to it. Liner, L-I-N-E-R. So the first condition is to check the residual plot to see, is there a curvature in the residuals? We need the relationship to be linear, or else the assumption of this test is flawed. So a residual plot just shows you the residual values across the whole range of the x values of the scatter plot. And so for a scatter plot that describes a real linear relationship, you might see something like this. Here's a scatter plot. Here's a visualization of the residuals in the residual plot. And you'll note that this looks like it's a good fit because the linear model captures the trend. There's only random noise left in the residual plot. There's no real pattern there. So this is a good indication that a linear fit is pretty good. Well, what about this data? If I go ahead and fit the least squares regression line on this, you'll see that if we visualize just the residuals on the y-axis using a residual plot, there's a pattern there. The residual plot zooms in on the curved pattern that we can see in the data. That curvature is not captured by a linear model. It's not just random scatter left. There's a pattern here. This violates the linear condition. It tells us, hey, a linear model is not good for this, so our condition will be violated. So let's go ahead and look at our data, our least squares regression line, and the residual plot. We're looking at the residual plot, and there's no real curve pattern here. If you see a curve pattern, you have to really see it. Here, there's not so much. It's pretty random. We'll say that this suggests a linear form. Independent. For this condition, you want to check that one, either each data point is independent, so knowing the value of one response doesn't provide information about another, or the sample size has to be less than 1/10 of the population size. So we're going to check that condition because in this case, it's not clear inherently that one nation's gun ownership or gun homicide rate will be independent of another's. So let's check this condition. So my sample size is 19, which should be less than 1/10 of all developed nations, since I'm sampling from the population of all developed nations. And even though there are more than 190 nations in the world, there are not over 190 developed nations according to how we define developed nations. So this condition might actually be flawed. So we're going to say we're going to proceed with caution. And on the AP exam, whenever you check a condition and it seems like it might not fit, just say, I'm going to continue, I'm going to proceed with caution, because you want to show the graders that you can still perform the test. In this case, violating this condition won't pose huge problems statistically for our tests, but we just want to note that this is a potential issue. So the normal condition, you can check one of two things. Either the distribution of residuals in the histogram has no major outliers and no strong skewness, or your sample size is greater than 30. Well, our sample size is 19, which is less than 30. So let's check the first condition here, first condition option. Looking at the histogram residuals, and I'm not seeing, there's a little bit of skewness, but it's not hugely skewed, and there's no huge outliers. So I'm going to say there are no outliers and no strong skewness. So we're good to go on this condition. Then equal standard deviation. Equal standard deviation residuals, you want to check the residual plot for my favorite word in statistics, heteroscedasticity. So here is the scatter plot showing a potential trend with what we call heteroscedasticity. And here's what you would see in the residual plot. You'll notice this funneling effect, where if you look at the low X values, the residuals are fairly small, but at the high X values, the residuals are fairly large. So there's variation in the residuals and the error as X increases. This violates the equal standard deviation condition. There is an unequal standard deviation as we proceed along X, and so this would not work. This is what we call heteroscedasticity. Hetero meaning different, scedasticity meaning variation, so different variation across different X's. So let's check that equal standard deviation condition here. We see again our residual plot. I don't see a very strong funnel. It's not perfectly equal across all the data points, but it all fits within this general range. And so I'm going to say it's good enough. The residual plot shows fairly similar scatter with slightly more variation at higher gun ownership rates. But overall, it's good enough for us to work with it. And then finally, the last condition, random. The data must come from a random sample or randomized experiment. In this case, the 19 countries that we sampled were randomly sampled from a list of all developed nations. All right, we checked the conditions. Now, let's go ahead and do the do phase. For our interval, we're going to compute the interval and report degrees of freedom. We can go ahead and get the confidence interval by plugging in the values shown here from the regression output table. And then we're going to get T star, the T critical value. Degrees of freedom is always a sample size -2 for regression. So we're going to do our inverse T command, getting an area of 0.025 because we want 2.5% on each tail. And we see that our T star is 2.11. So we end up getting this confidence interval. And then for the significance test, we're just going to simply report the test statistic and the p-value as reported in the regression table. So we're going to write down, here's the test statistic, the t-test statistic, here is the p-value. And note that the p-value shown is always going to be the two-sided p-value. And so if you're doing a one-sided test, you're just going to want to divide this by 2. And then finally, the conclusion phase. For an interval, we're going to interpret this interval with context. So we are 95% confident the interval from -0.01 to 0.10 captures the true regression slope for linear regression relating developed nations' gun ownership and gun homicide rates. For the test, we're going to reject or fail to reject. We're going to look at our t-value, our p-value, and we're going to say because our p-value is greater than our alpha, we fail to reject the null hypothesis. We do not have convincing evidence of a linear relationship between developed nations' rates of gun ownership and gun homicide. So that brings us to our discussion. We did not find convincing evidence in our data set of a relationship between rates of gun ownership and gun homicide. And this conclusion, based on the data that we have here, makes sense. The relationship was very weak. But note that this data set was gathered and shown without the United States. If we were to visualize the United States on here, here's where it would be. The rates of gun ownership and the rates of gun homicide are way higher than any other developed nation from our data set. So would reducing civilian gun ownership also reduce gun homicide in the US? What do you think? And explain your reasoning. Now, I want you to try and answer this from 3 different viewpoints. First, answer this question using only the data we've analyzed without making any assumptions. Then answer by choosing a clear side and use a BS or bad statistic argument to support it. Third, provide your actual personal opinion and make sure, as always, to address the data we've covered. So that brings us not just the end of this lesson, but the end of our whole AP Stats video series. And statistician to statistician, I have some final advice for you all. When analyzing data, be critical, be cautious, be compassionate, and as always, avoid BS, bad statistics. I hope watching has helped you gain some new perspective on how we can analyze data and how we can analyze the world around us. Goodbye, statisticians.